Assalamu alaikum. Today we are going to discuss about one of the most popular paper of computer vision, and you can say that it is one of the most favorite paper of natural language processing community as well. And it is the basis of next generation of deep learning in which transformer models are being used by various researchers, and currently people are working in deep learning community are looking forward to understand the basic pipeline or the basic structure of this model. So today we will try to understand what researchers or the authors of this paper, Transformer, Attention is All You Need, are trying to tell the research community. So you can find the video at the link at YouTube link, and you can download the presentation from my GitHub link. So let's dive into this paper. The title of this paper is Attention is All You Need. And this is the basic structure of transformer model. So we will see why people started to work in transformer and started to use transformer model. So before transformer, there was a deep learning model known as recurrent neural network, and it was considered to map the long-term dependencies. But there are certain downfall, or there are certain drawbacks of using recurrent neural networks. So how the recurrent neural networks work, it will take the input state, and then we pass this input state to recurrent neural network. It work on the first input and combine it and form the output, that is Y1. For the next input, for the next state, the next state output is computed using the next state input and information from the last recurrent node, and then they produce Y2 as an output. Then for the third input, the third output has been produced using the third input and the initial state of previous node. And that is how the third input is dependent upon its previous state output and input, and the transformation function that is being applied by recurrent neural network. So you can see that its dependency is on the last previous state, not the entire state or the entire transition of states of recurrent neural network. So this type of model faces some challenges to map the long-term dependency. It can map the short-term dependencies, but not suitable to map for long-term dependency. That's why these kind of models are not very popular in video processing tasks, in which we have a series of frames where we want to model the actions and map it. So that was the prime problem in recurrent neural network. So we can study one by one what the problems people were facing by using recurrent neural network to model their time series data. First of all, it is slow in computation for long-term sequences and cannot able to map the accurate long-term spatiotemporal information. It also suffers the problem of vanishing gradient. So if we try to see how vanishing or exploding gradient problem, which is one of the most important concept in the field of deep learning, where we always try to avoid this problem while training our model. So your PyTorch or TensorFlow always work on the principle of removing the problem of vanishing and exploding gradient. So TensorFlow and PyTorch try to make the computational graph to represent the process of converting the input into its output. For example, if we have two inputs, that is X and Y as your input, you feed it to your model, and model performs some kind of transformation on it, and you can call it, this is the transfer function. This is the transfer function of f of x, comma y. And you can see the function or the transformation function is basically the dot product between x and y. And it will produce an output which is also a function of g. We can see that is g of x. We can say it is g of z, and it might be like z square. And the output is basically z. So in deep learning, while we in feed forward step, while we move forward, we compute the transfer function and transform the inputs to output. While computing the in backward phase, we try to find the loss, try to improve the model, try to adjust the weight, and we try to map the output to as close as possible to our ground truth labels. So while we compute the loss of this output with respect to its input x, so how we can represent it? We can represent it as d of g. G is basically our output. And with respect to, we are finding the loss with respect to input x. So d of x is basically equal to d of g by f of x, the transfer function, multiply by d of f with respect to x, because x is the input. So these two terms will be cancelled and it will find out. So consider that this term, if we're trying to compute it, if this derivative of g of x, d of g with respect to d of f is equal to 0.5, and this term d of f with respect to x, d of f with respect to x is also 0.5. So this is equal to half, and we multiply it with half. So both half, when we multiply it, its value become more lower than its input, single input, like it will be equal to 0.25, which is more smaller than this 0.5. So the concept of vanishing gradient means that if these nodes become, there is multiple nodes that are in between the input and output, and we have the value of these derivatives are lower than one, then at the end, the derivative becomes negligible and it's become equal to infinity. So it will create, it won't be able to reduce the loss either, but it will create the problem of overfitting and underfitting. And in exploding gradient means like these value become higher than 1. If its value is larger, its amount is so large enough so that our model cannot able to obtain its global minima but stuck in local minima. So that is how these problems are being present in recurrent neural network. So next problem is difficulty in accessing information from long time ago. Like if I'm talking about the video frames, if we have video frame 1, video frame 2, video frame 3, in case of videos, if we have video frame 1000, it's very difficult for the RNN to map the change or the semantic or contextual information of the videos from all the frames. So this is the prime problem that is present in the recurrent neural network. So that problem helped the community to identify, the authors to identify a new model that is known as transformer, which is attention all you need. So this transformer model consists of two micro blocks. First is the encoder block and the second is decoder block. And we will study how these two blocks, that is encoder and decoder block, help in making the information to capture from long-term dependency, avoid the problem of exploding and vanishing gradients, and it is simple to compute the information of temporal sequences. So let's see how it helps in mapping all the information. So first of all, before starting understanding the paper, let's see the possible notation we are going to use in entire sequence. So for example, we have a matrix. And this matrix is basically having a dimension of the sequence length is 6 and the D model is 512. So it's a simple matrix, means that there are 6 rows that are present in this matrix. 1, 2, 3, 4, 5, and 6. 1. So that is A, B, C, D, E, and F. So these are the rows, and there are 512 columns that are present in this matrix. This is 1, 2, 3, all the way to 512. This is 512. Okay. Similarly, if we have another matrix, which is basically the transpose of the first matrix, and in this case, we have 512 rows and we have 6 columns. So 6 columns mean that this is 1, 2, 3, 4, 5, and 6. So this is column A, B, C, D, E, and F. And these rows are from 512. So this is the same matrix, but only the transpose form of this matrix. So if we find the dot product between a matrix, whether it's transpose, so we have 6, the dimension is 6 and 112, and we multiply with a matrix. For example, this is a matrix A, and we multiply it with its transpose, that is A prime, and it is basically 512 by 6. So the resulting matrix is basically of dimension A by A dash is equal to 6 by 6. So if we multiply the first row with first column, then second row with second column, we will get a matrix whose dimension is having 6 rows and 6 columns. So that will be AA, will be AB, that will be AC, and so on. So that is one of the intuition that is being given in the paper, that if we multiply a matrix with its transpose, we get the external dimension, that is 6 and 6. Okay. So we will discuss about the encoder block in the first step, and then we will discuss how the decoder block will process the input. So in encoder block, the first we will discuss about the input embeddings. So for example, if our input is this sentence, so in first step, we will tokenize our sentence, and our sentence is, your cat is a lovely cat. So we will tokenize our sentence into a word level token. So there are some transformers that have the capability to further tokenize a word also, but we are not going, for simplicity, we are not going to discuss about them. We are tokenizing a single word level token. We obtain the token equal to the words that is present in a sentence. So initially, we will tokenize the sentence, and then each sentence, each token is being represented by an input ID, which is being assigned in a vocabulary. So English vocabulary have a fixed ID that is being assigned to your, fixed ID that is assigned to cat, fixed ID that is assigned to S, and this ID can be changed for other language, like Chinese language have their own IDs for their words. So in English, your word is being represented by 105 ID. So you can see that cat is appearing twice in the sentence, and the ID, that is 6,587, remains same in both of them. See? So in next step, after getting the value of input ID, it will generate an embedding vector. So this embedding vector may vary with respect to the type of transformer you are using, and transformer will adjust its weight depending upon the input that is being provided to it. So these value is not fixed. It will change with respect to transformer and with respect to ID, with respect to the input that is provided to the transformer. So this ID is being converted into an embedding, and these are the learnable parameter of your model. So it will assign a representation of 512 vector size. So the D model is basically 512. Like length of this embedding is 512 for each word. So after computing the embedding, the positional encodings are being computed for these words. So what is positional encoding? We want each word to carry some information about its position in the sentence. So we want to make the words have temporal dependency with each other. So that's why we use positional encoding to carry the temporal information with themselves. We want the model to treat the words that appear close to each other as close as possible, and the words that are distant from each other should be as distant as possible. So we want positional encoding to represent the pattern that can be learned by the model. So your transformer model has the capability to recognize that these words have temporal and contextual dependency with each other. So that's why we apply positional encoding after applying the simple encoding. So your sentence, that's how the transformer will work. We will input this original sentence. It will tokenize it. It will find the vocabulary IDs. The IDs are being converted into a vector embedding of size 512. Why 12? Because D model we are using for this transformer is D 512. That's why the embedding is 512. Then positional encodings are being computed, and these encoding are only computed for the ones, and it will save for next time. For the next sentence, the first token have the same positional encoding. The second token for the next sentence have the same positional encoding. So that's why the model computed the positional encodings first, and then it will save it and it will remain same for the next sentences as well. So these encoding are being concatenated with positional encoding to form encoder input. So that is how positional encoding or encoding is being calculated for transformer. So this is the formula that has been given in the paper to compute the positional encoding. And we see for odd number, this formula is being used by the authors to compute the positional encoding. 2i is basically the position of the embedding, and D model is your model. So that is how it's able to compute. And for this is basically for the odd positions. We only need to compute the position encoding once and then reuse them for every sentence, no matter if the training is present or not. So this is the visual representation that is given in the paper to show that how positional encoding. So this is basically the depth, which is 2i. And this is the position, that is pose, that is present in the formula that we displayed previously in the slide. So that is how you can see that each position have its own representation in the model. Trigonometric function like cos and sine naturally represent a pattern that the model can recognize as a continuous, so relative position are easier to see for the model. By watching the plot of these functions, we can also see the regular pattern, so we can hypothesize it. So that is how this encoding, this part is being completed with computing the tokenizing, calculating the vocabulary IDs, converting them into input, embedding, concatenating it with positional encoding, and then now we move towards the encoder block. So in encoder, we will first discuss about single head attention, and then later on we will discuss about multi-head attention. So we will talk about the self-attention. So self-attention allow the model to relate the word to each other. So its purpose is to find the relation between the words with each other. It is simple case we can discuss the sequence, that the sequence length is 6. So this is the sequence length. This is the notation we are going to use. D model is basically DK, having 512. And this is the formula they have used for computing the attention, that is attention Q, key, and value, and then computing the softmax from query and key, and transposing the query key and multiplying it with value. So let's see how they have computed it. So they computed the softmax of query and key. And then after computing, as we already discussed, that if the dimension is 6, 512 and 512, 6. So if we find the dot product of this, we will get the outer dimension, that is 6 by 6. We will obtain a matrix of 6 by 6. And you can see that these diagonal have the maximum value, and these are used to represent the attention. So if we multiply your with your, so this is more related with one another. Cat is related with cat, so it has more value, or attention span is maximum over here. Is so if you want to mask out, or if you want our model not to see any specific word, what we are going to do, we will replace this value with minus infinity, so our model would not able to see this value, only depend on certain value in which we are interested. For example, the attention mechanism means, like, if we have an image and we want our model to see only there is a skin part, and in skin part only this part is infected by melanoma and this part is infected by melanoma. So what we do is we find this representation, and we only try to make our model to have attention on this part of this image, and rest of the pixels have the value of negative infinity, so that our model cannot able to give attention to other pixels which are not important. So we precisely inform our model that this part is more important for us, rest of the model. So when an input appears, so our model only see the melanomic part and try to extract features from only that part. So that is how we can able to utilize our model to give attention to only specific part, and this is known as self-attention. So you see that in self-attention, what we are going to do is we have the softmax part, this matrix in which we have provided the attention and we multiply it with our value. So when a matrix multiply with another matrix, only the outer dimension are being left. So 6 by 512, the resulting matrix after applying the matrix multiplication, it will be 6 by 512. Each row in these matrices capture not only the meaning, positions, but also the part that is more important, and that is known as self-attention. So there is basically the interaction of each word with all the words that is present in the sentence, and that is how we are giving attention to our model, and this is self-attention. So there are certain properties we would like to discuss about what are the prime properties of self-attention. Is that self-attention is permutation invariant. For example, if I computed this matrix, that is of the matrix that is computed after attention, and I have a matrix that is having a row A and B, C, and D. And after some time, if I computed the attention for some time later for similar input, and this is basically my self-attention A prime, B prime, C prime, and D prime. So if I change the position of my input, like B is change its row and C come upper hand and upper row. So the author says that the value of this attention won't change, only the position will be changed, not the value of self-attention. So that is the property of self-attention, that it is permutation invariant. So next property is that self-attention require no parameters. So there we haven't talked about any kind of parameters so far. So this is the quality of transformer, that it won't require any parameter. Up to now, the interaction between the word has been driven by their embedding and positional encoding. This will change later. We expect value along the diagonals to be highest because these are interacting with their own self for their attention. So these diagonal must have the maximum value, like they correlate with one another with maximum as compared to rest of the sentence. If we don't want some positions to interact, we can always set their values by infinity. Like we can mask it out. We will mask out those values if we want our model not to see. And similarly, while training, we want our model not to predict the next word. Instead, we want our model to see the data that is being provided to it. So we want to make it a causal system. Causal means it will only see the events that happen in the past, not the future. But if we train our model for previous data, the data that is being provided to it instead of future, it has the capability to map or find the temporal information, and it can able to predict the word in future. So that is the property of self-attention. So it is temporal. So if we don't want some position to interact, we can always set the value to minus infinity before applying the softmax in this matrix. And the model will not learn those interactions. And we will use this in decoding. So these are the mathematical representations or mathematical expressions that are being present in the paper, and they have used the attention, the mathematical representation for attention and multi-head attention. Now we will discuss how multi-head attention will work. First of all, input of sequence length is being provided, and this model have the embedding with D model embedding. Sometimes it is also known as DK and DV. It is also represented as DK and DV. And then H is the number of heads. So this input, for example, this sentence sequence is being move towards to find the vector embedding, and then these vocabulary IDs are being converted into embeddings and added by positional encoding. So this input is being are being replicated and feed to multi-head attention. This is having the same matrix having as key, query, key, and value. So it replicated into three metrics, that is query, key, and value, and then this input is being fed into add norm layer as well. So we will see one by one. So next is we have an input sequence of sequence length and D model, and we form the three representation, replicate this input into query, key, and value, and it's have the same dimension that of our input. So this is sequence by D model. So next is we multiply it with some weight, and which is this weight is equal to having dimension D model by D model. So if we multiply a matrix with another matrix, so the output will be equal to sequence by D model. So this will be the Q prime, K prime, and V prime. So this Q prime, K prime, and V prime are being further passed to multi-head attention, and this multi-head attention is divide this Q prime, K prime, and V prime into Q1, Q2, Q3, Q4, K1, K2, K3, K4, V1, V2, V3, and V4. So it divides the sequence by D model into small parts based on D model. So D model is 512. So in this example, the embedding size is 512, and we have 4 heads. So we divide it with 4. So each part is basically representing 512 divided by 4. So that is basically DK. DK is the small part of our embedding. So we have this D1 pass concatenated with K1, V1, and it will form the one head, H1, H2, and H3, and H4. So this is basically when combined, and this DV is basically when it's combined, it forms the D model, that is 512. Basically, it is the subsection of our embedding, and we want that our heads, that this head see the entire sentence, but only the small part of it. So the head contains the entire embedding, but the head one will only see the small part of the embedding. So we can visualize the attention, like if a sentence is being given, the more attention is being paid at uh, specific annotation, like making. Making have more attention to its own word, that is making, and have least attention to rest of the words. More making and more have some contextual and temporal dependency with each other, and difficult have also some dependency. So that is how we want our heads to see the small part of the sentence and give attention based on the information. Like in some languages, one word can be act as a noun. In some sentence, it can act as a verb. In some sentence, it acts as an adjective. So we want our heads to be independent of entire sentence rather to see only the small part of it and try to drive some context and temporal dependency between the words. So then this head is being multiplied with W naught, having head DV and D model. So our the resultant multi-head attention sequence will be sequenced by D model, which is the input embedding that is being feed to the model, that is sequenced by D model. So our output will having all the temporal and contextual dependency with within the small part of the sentence. So we can consider this value with some example, like for example, we have a key and a value. Like in Python, we have a dictionary which holds the key value pairs. Like we have a movie which is romantic, we divide this movies into some categories. Like romantic is one category, action is another, science fiction movie, then horror and comedy, and we assign this class, like Titanic is a romantic movie, action Dark Knight is an action movie, Inception is science fiction, horror is The Shining, and comedy is Intouchable. So these are the key and along with the value pair. So what transformer will do will identify like this class belong to this value. It will find the embeddings, map it, train itself, and then when a query appear, which is not the part of this key value pair, but it will try to see the contextual dependency with one another. So it will try to identify which is the most suitable class or belonging of this category. Like love belong mostly with romantic. So it will map this word to romantic class. So this is the effects or attention that is being given by transformer. Like romantic have more uh, temporal and contextual dependency as compared to comedy and rest of the classes. So transformer will map it to romantic class. So this is basically the encoder. We pass this query, key, and value of our training set, and it will pass to multi-head attention. It will normalize it and then pass to feed forward layer to add some linearity within it. And then we see that the layer normalization, its job is to normalize the information or the embedding that is being passed after performing the multi-head attention. So the learnable value in these parameters are gamma and beta, which is multiplicative, and beta is additive. So these value will also learnable by the transformer, and it will help to make the information more normalized, more beneficial for the model to learn the way. And then comes the decoder block. Now, decoder is taking the key and value pairs from the encoding and query from the input. So it's taking, because query, that is unseen input having only the value. That query part is been coming from the test set. So this will form multi-head attention, and then it will assign the softmax probabilities to possible class of the model. So mask multi-head attention, it will remain same for both encoder and decoder. It will perform the same operation that we have recently discussed. Like it will compute the embeddings at positional encoding, compute multi-head attention using the D model and DK, and form divide the embedding into DK and add normalization, and then take the key and value from the encoder part and query from the input that is being provided by the user. So what is mask multi-head attention? Our goal is to make the model causal. Like I already told you, we want our model to see only the data that is being provided during the training stage. So what we do, we will try to see, like if we have this input, like your cat is a lovely cat. So your, so this is the first word. For to make it a causal model, the next word, we don't want our transformer during the training phase to see the future word, but it can only see the word that is provided to it. So during the training phase, it only see the first word. Then for rest of the sentence, we make it negative infinity so that it won't be able to see rest of the words. And when the next word appears, it can map the previous temporal dependency and spatial dependency between the sentences. Like cat. Cat is the next word. It will find the attention whether it's your. So your and cat are not related to each other. So that's why its value is 0.124. And then when cat we find the attention or multi-head attention with cat, it has maximum value as compared to your, and rest of the word as they are not seen by the model, so we make it minus infinity, and it won't be able to see the future words during the training phase and make it to the causal. And this is the third, so it can see only the words that is present in third place. So is not related with your and cat, but it is related with is. So the correlation between is maximum as compared to previous two words. And similarly, this diagonal must have the maximum value, and at the end the model can able to see the entire sentence, and we don't have to apply any infinity mask or mask it attention. So we see that if we make the transformer model causal, so it can have the capability to forecast the value once in the predicting time. But during the training time, we try our model to only see the data that is being provided to it. So we have discussed, so far we have discussed this, like we have input, we replicate this input into query, key and value, multiply it with weights, and that is D model by D model, and we get Q prime, K prime and V prime. Q prime is basically sequence by D model, K prime is sequence by D model, V prime is also sequence by D model. Then if we, depending upon the number of heads, if we have 4 heads, we divide the D model into dk into divided by 4. So this dk Q1 plus K1 plus V1 form the head 1, head 2, head 3 and head 4. And when we combine these heads, we will again get the head, which is sequence by head into dv. Dv is similar to dk, but in the paper they have written it with dv, so we are also using dv. And then this dv is being multiplied with wo, which is nothing but a weight, that multiplied with our head or attention to make it multi-head attention. And the resultant matrix, which is multi-head attention matrix, is equal to sequence by D model, which is the similar as the input that we have provided to it. So all the above value in the diagonal are replaced with negative infinity before applying the softmax, which will replace them with 0. So this formula will help us to mask out the words that are future words, and this will help the model to only see the data that is present in the past. So at the inference time, let's see how the model will work. Model will train encoder part using the embedding received from key, query, key and value. After training, the decoder part will take the key and value. So decoder will feed key and value pair to decoder, sorry. So decoder will take these two matrices from the encoder part. This is based on your data set or your training data. And the decoder will compute the embedding of the query and using this key and value pair to map this query to possible key value pair. In this way, it can able to find the possible class or anything using the training data. So for example, if we are working on the translation part, in which the sentence that I love you very much is being translated into French, and the translation for this sentence is "ta amo molto." So how the decoder and encoder will map it? Let's see. In the first step, these tags are being added: start of sentence and end of sentence. These tags will help the transformer to know that sentence is being started and here the sentence is going to end. So this language that I love you very much is being imported to encoder, and encoder will find the encoding embedding using the positional encoding and vector vocabulary, and then find the embedding using sequence by D model. It will pass to encoder. Encoder will output its sequence by D model. So here key and value are being fed to the decoder. decoder will already have this vocabulary with it, and what it will do, it will pass to the decoder. Decoder will map this English to French vocabulary, find the embedding, try to decode it. Query will find the embeddings, pass it to the decoder. It will find the multi-head attentions. It will see which words are mapped to which words of French. Like this word is being mapped to having maximum attention with these words. So it will find the maximal multi-head attention with these words. After mapping these embedding having positional encoding and vocabulary embeddings, and then it will find the attention and maximum probability. Using maximum probability, it will find which words having maximum attention, and then we apply linearity with it and apply the softmax to further verify the probability. So this cross entropy loss is being used to map the word to respective translation in the French. The encoder output for each word and vector that are not only capture its meaning embedding but position, also its interaction with other words by meaning and multi-head attention. So at start of the sentence, it will help the model to see like start of the sentence. So it will automatically add start of the sentence. Then it will find the possible embedding which having the same maximum attention head and try to translate it. So we prepare start of sentence token at the beginning. That's why papers say that decoder input is shifted to right. So we select a token from the vocabulary corresponding to the token with maximum value. The output of the last layer is commonly known as logit. So the last layer, the output that is being generated by the softmax layer is known as logit. Both sequence will have same length. So how can we use that by the help of padding? Since decoder input now contain two tokens, we can select softmax corresponding to second token. So use encoder output from the first timestamp. So we select at every step that word with maximum softmax value. The strategy is called greedy and usually does not perform very well. A better strategy at each step is top B word and evaluate all possible next words to them at each step, keeping B the most probable sentence, and beam search strategy is being used. So thank you so much. I tried my level best to make the internal mechanism of the softmax, internal mechanism of the transformer as simple as possible. So thank you so much.